Hello guys, welcome back to Farhad's website. In previous lesson, I explained the universal law of gravitation. We explained this law that focused on two things especially. It focuses on, let's say, on the product of masses, of two masses, and the distance between the centers of these masses. And you know the relationship between the, let's say, force and, let's say, product of mass and force, gravitational force and the uh, distance. Actually, gravitational force is directly proportional to the product of the interacting masses and inversely proportional to the, let's say, square of the distance between the objects. This is a summary of the previous lesson. Just I wanted to jog your memory. Right now, I prepared some questions have to do with the gravitational law of, let's say, universal law of gravitation. Let's dive in with the lesson by reading the question. Question number one: planets move in space orbits around the sun. We have some options here. So planets move in circular, nearly circular, elliptical. B and C are correct. And in previous lesson, I told you Galilei believed in perfect circular for orbiting the, for let's say, for orbits of the planets. But who corrected his mistake? Actually, Johannes Kepler corrected his mistake. He said that the let's say, orbits of the planets are nearly circular or elliptical. They are oval, yeah. Orbits are oval, not let's say circular. So circular is not, let's say, accepted. Nearly circular means oval. It can be like this, right? X shape, elliptical, no problem. So B and C are correct. So uh, if Galilei, let's say, were right, if let's say orbits of planets were, let's say, perfect circular track, actually seasons would not create, and let's say we would have only one season, let's say, in a whole year. That's why, let's say, it doesn't, let's say, coincide with the four season, right? Right now we have four seasons uh, in a year. Actually, every year, let's say, contains four seasons. That's why the orbits of the planet actually must be oval or elliptical to, let's say, to coincide with the with our life, right? That's why Kepler, let's say, corrected the mistake of Galilei. Number two, question number two. So the option, yeah, I chose the D for you. Question number one. Question number two: the force that keeps the planets from coasting off in a straight line is. Coasting off means eject, actually, slide, right? Actually, objects, let's say, or planets don't coast off, let's say, don't coast off actually in a straight line, right? Objects or planets keep moving about the sun, right? Planets in general keep moving about the sun. They don't coast off in a straight line because of gravitational force. So the force that keeps the planets from coasting off, this force prevents the planets, let's say, from coasting off in a straight line. This force is it called a centrifugal force? No, we don't accept centrifugal. We rejected it, actually. Inertia? No. Inertia, actually, tries to eject the planets from, let's say, from its circular track. Inertia tends to coast off the planets in a straight line. That's why it can't be actually inertia. Frictional force, is it friction? Is there any friction between the planets? Do planets collide with one another? No, it's a very dangerous situation, and it doesn't happen. Let's say these days, actually, this era that we live, it doesn't happen. Maybe in a future, in a, let's say, far future, this let's say phenomenon happens, and on that day we don't exist actually, because our life is limited. That's why this one can't be. So the only answer is gravity. Gravity keeps the planets from coasting off in a straight line. Gravity keeps the planets in a, let's say, in its orbit, in their orbit. Gravity, let's say, tends to give this elliptical orbit to the planets in general. Number 3, it's the force that keeps the planet from coasting up in a straight line. It's the same, let's say, same question, same concept, but options are different, right? Centripetal force, it's right. Field force, teacher, what do you mean by field force? Field force means forces act from afar, right? Objects don't collide, let's say, with one another, but they affect one another from afar. So gravity is one of these forces. Magnetic force is one of the field forces. That's why gravitational force it can be, and gravitational force is a field force. It acts from afar, right? Gravitational force becomes a centripetal force. So these expressions coincide with one another. Either you say centripetal force keeps the planet from coasting off in a straight line, or you can say field force is a field force. There's a field force that keeps the planet from coasting off, or gravitational force. So all of the options are true, right? Number 4, gravitational force depends on what? Based on the Newton's universal law of gravitation, it depends on what? Right. Size and composition of objects. Is it right? Does gravitational force depend on size? No, I told you. Size and composition don't matter. Mass and distance is true. Mass and distance. Faces of object? No, it doesn't matter actually. Face, whether the object liquid, solid, or gas, no problem. All of the previous factors. No, only mass and distance. Number 5, gravitational force is gap force, is a space force. Fill the gap for me. Gravitational force is an attractive contact force. Contact means against the field. Means, let's say, force, let's say, during the exerting of force, objects collide with one another. Does it happen in gravitational force? No. So the first part is true. It's an attractive force, no problem. Gravitational force is an attractive, but it's not contact, it's a field force. B, a repulsive field. And so this option, the first part is wrong, because gravitational force never be, let's say, repulsive. It's, let's say, it's attractive forever. That's why the second part is true, but let's say the wrong part counteracts the right part. That's why we don't accept it. See, an attractive field. This one is nice. This one is true. Attractive, gravitational force is attractive, right? Yes, and it's field force. It acts from afar, at a distance, right? A repulsive force, a repulsive contact, no. So the only option is C. Right. Let me read another question. Question number 6. Let me read it for you. True, false sentences, right? True, false statement. Let me read it for you. Planets circle the sun in elliptical orbits. True or false? Of course, true. Who said this? Johannes Kepler, right? Elliptical means oval, egg shape, semicircular. It can be semicircular or nearly circular. It can be. Planets circle the sun in circular orbit. It's false, yeah? It's false. We don't accept it because of the orbit. Planets circle the sun, no problem. They orbit the sun. But the path is problem here. The problem is, let's say, circular is not, let's say, that's what the first part is true, but the second part is wrong. All right. Question number 7 is true false statements as well. Gravitational force is directed along a tangent to Earth's surface. Is it right? Gravitational force points to the tangent, points to the tangent to the circular, to the surface of Earth. No, it's false. Gravitational force, another, let's say, statement, gravitational force is directed toward the center of Earth. Of course, this one is true. Gravitational force, let's say, points toward the center whenever you, let's say, you let this marker go. So where does it go? It points, let's say, toward the center of Earth. It goes down. That's why the direction of the gravitational force is toward the center of Earth, downward. Question number 8, according to Newton's space, yeah, we have a gap here. According to Newton's law, FEM is equal to negative ME actually, where FEM stands for the Earth gravitational force on the moon, and FME represents the moon's gravitational force on Earth, right? So fill the gap for me. According to Newton's law, these forces are equal in magnitude, opposite in direction. Can I say one of them is action and the other is reaction? Yes, action and reaction, equal in magnitude, opposite in direction. That's why this law can be a Newton's first law or Newton's second law or third law or Newton's universal, let's say, gravitation. I'm sure you know the answer. So this is the Newton's third law, right? Let me read the question number 9. Read question number. Newton's gap states that the force exerted on Earth by moon FME is equal in magnitude to and in the opposite direction of force exerted on the moon by Earth, right? FM. So this one is Newton's third law or Newton's second law actually. Of course, this is the same. It's let's say they are similar. These questions are similar. So this is the third law of Newton. Let's move on to another question. Question number 10. Let me read it for you. Number 10. Gravitational force is space proportional to the product of the object's masses. Is gravitational force, let's say, is the gravitational directly proportional or inversely proportional to the mass? Actually, this is the numerator of the universal law. Fg is equal to, let me let's say remind you this rule. Fg is equal to G capital M1 M2 divided by R squared. So let's say because it talks about the masses, that's why it must be directly proportional. Fg is directly proportional to M1 and M1 M2 means product of masses. 11, gravitational force is space proportional to the square of the separation between objects' mass. Separation means distance, right? So it talks about the distance, right? Talks about the distance or R. So gravitational force, which kind of relationship is there between Fg and R? Of course, inversely, right? You have to circle inversely. Question number 12. The value of G, and by the way, this is the question of national exam, right? The value of G in equation Fg is equal to G capital M1 M2 over R squared is equal to which of the following? 6 times 10 to the power negative 19, Newton meter square over kilogram square. 6.3 times 10 to the power negative 23, right? So the units are correct. The units of all, let's say, all options are correct. Newton meter square over kilogram square. But let's say you have to focus on the value of the numerical value of the constant. Is a 6? No. Is a 6.3? No. 6.673 is an accurate value of G actually. This one 6.63, no. So this one 6.673 times 10 to the power negative 11 Newton meter square over kilogram square. C is true. 13. The law of universal gravitation is an example of space law. Which type of, name this, let's say, law. Does it belong to the only square law? No, it's strange. We are not familiar. We are not familiar with this phrase actually. Inverse square law is true. Inverse square law. So this option is right. Question 14. Why is the law of universal gravitation an example of inverse square law? Why do we name, let's say, universal gravitational law? Why do we name it as, let's say, inverse square law? Because, let me read the answer for you. What's the answer? And I'll explain it for you, actually. Why do we name the universal law of gravitation, let's say, as, let's say, inverse square, as an inverse square law? Because the force varies. Look here. Because the force varies as the inverse square of the separation. So focuses on, the question focuses on the equation. Because the force varies or let's say, changes as the inverse square of the separation. In other words, the force between two masses decreases as the masses move farther apart. Imagine moon, let's say, moves away from the earth and the distance becomes twice, right? Let's say, does the amount of gravitational force between the earth and moon remain, let's say, as it is or not? It doesn't remain as it is, because separation doubles. Whenever separation doubles, forces decreases to what? Forces decreases to, let's say, 1/4, based on this equation. Look here, Fg is equal to G capital M1 M2 divided by R squared. So let's say, I told you an imaginary, let's say, case, right? I, let's say, gave you an example of when the moon moves away from the earth and the distance becomes double, right? In this situation, R becomes what? R becomes twice, right? Don't care about the mass and because mass of the planets and the moon are constant, and this is constant. So focus only on R, right? So Fg, only I focus on this, is inversely proportional to R. I said R becomes double, separation becomes twice. So write 2 here, and let's say R is square, so gravitational force will be 1/4, right? So it decreases 4 times. It decreases to 1/4 of the, let's say, original value. That's why, let's say, we name it as an inverse square law. Question number 5, gravitational force between two masses, space as the masses move farther apart. Complete the gap with one of these options. Gravitational force between two masses, does it increase? Does it decrease? Or does not change, or doubles when the masses move farther apart? I told you, based on this, let's say, equation, Fg is inversely proportional to R, right? Fg is inversely proportional. So let's say, the farther the object is, the less the force is, right? The greater the separation is, the less the gravitational force is. And that's why decreases, force decreases is true. Number 16, Fg is equivalent to, Fg is equal to what? Which, let's say, question is, which option is true? Fg is equivalent to weight of an object. Yes, it can be. Fg is weight of an object. B, G capital M mass of Earth, mass of object divided by r squared. It can be. It's true. C is equal to mg. Mathematically, weight is equal to mg, right? Fg is equal to mg. That's why all of the options are true. This question number 16. Let's move on to another question. The next question is question 17, which is the question of national exam. This question is and question number 18, question number 20 also, they are questions of national exam, right? We have, let's say, 4 or 5 more questions to finish this lecture actually. Question number, let's say, 18G, and by the way, I told you this is the question of national exam. 18G in the equation, Fg is equal to G capital M1, M2, let's say, divided by R squared is called, yeah, I think I didn't read question number 17. Yeah, question number 17. Excuse me, I missed question number 17. Let me read it for you. I'm sorry about that. Question number 17. Which of the following represents the unit of G in the equation? So G capital. What's the unit of G in this equation? And this is the question of national exam, right? Newton meter square over kilogram. Is it true? No, because kilograms are multiplied by one another. That's why it should be kilograms squared. It's wrong. This one is wrong, right? We don't accept this one. What do you say about, let's say, this one is wrong. What do you say about the Newton meter over kilogram squared, right? We don't, Newton meter over kilogram square. No, because meter should be square as well. That's why we don't accept it. Newton meter over kilogram. No, because neither mass nor kilogram, let's say, is squared. That's why it's completely wrong. So the only option is option D is true. Question 18, G is in the equation, and this is the question of national exam as well. G in the equation, Fg is equal to G capital M1, M2 over R squared is called what? Name G for me. Is it constant of universal gravitation? Yes. A. B. Coefficient of friction. It doesn't make sense actually. C. Gravitational force. No. D. Free fall acceleration. Actually, free fall acceleration, don't confuse it. Free fall acceleration is G small, right? And its value is equal to 9.81 meter per second square for our globe, right? For our planet. But G capital actually differs from G small. That's why the only option is A. Only A is true. 19 is the unit of free fall acceleration, G. Yeah, I mentioned it in advance. The unit of free fall acceleration, rad per second square, no. Meter per second square, yes. But I told you, don't, let's say, hurry, read the all options. After that, you decide. After that, guess the answer. Meter per second square, till now it's true. C, Newton over kilogram, maybe, yeah. Let me jog your memory. And D is equal to, D says B and C are correct. Let me write an equation. Think about Newton's second law. Newton's second law says that F is equal to ma. Force is the source of acceleration. Any motion is due to the external force. This is the Newton's second law of motion. So here, I want you to rearrange the equation for A, right? Because it says the unit of free fall acceleration. Or let's say A or G. Let's say turn it to G. Fg is equal to mg. So A, let's say, or G is equal to F over M. F over M. F force is measured in Newton and M is measured in kilograms. So Newton over kilogram is the unit of, let's say, free fall acceleration. That's why the option C is true as well. Beside meter per second square, acceleration due to gravity or any type of acceleration has this, I'm talking about the linear acceleration actually. Linear acceleration has the unit of Newton per kilogram beside meter per second square. That's why B and C are correct. Question 20, it says determine the change in gravitational force between two masses if the distance between them is doubled. This is the question of national exam, right? Let me show it to you. Question 20, 21, I think, or 20. Question 20, it says, determine the change in the gravitational force. What happens to the gravitational force? Does it increase? Does it decrease? When the distance becomes twice, when the distance becomes double, right? Let me underline it. Double means twice. So A becomes 4 times. When the distance becomes double, distance is increased. And distance and force are inversely proportional. That's why it becomes 4 times. The gravitational force does not become 4 times because objects, let's say, move away from one another. That's why it can't be. Becomes 3 times. No, it's wrong. Becomes 1 over 4. It's true, right? Because the distance doubles. And I told you, automatically, I want you to write this equation, this relationship, 1 over r squared. And it says the distance becomes double, becomes twice, right? Let's say substitute 2 instead of r. It can be what? So Fg will be 1 over 2 squared. It means 1 over 4. If, let's say, question says that the distance, let's say, is triple, for example, the distance becomes triple actually. In this situation, put 3 instead of r and square it, and it will be 1 over 9. But here 1 over 4 is true, and the last one does not change. It doesn't add up, right? That's why only C is true. Question 21. Gravitational force would be space if the distance between Earth and the Moon turned to what? Turned to half the original distance. If the distance between Earth and Moon turned to the half of the original distance, let me examine it for you mathematically. I told you, you have to write this relationship. Fg is inversely proportional to the r squared. Here it says distance becomes half. It turns to the half, right? Right, let's say put 0.5 here. Instead of, let's say, r, substitute 0.5 or 1 over 2, no problem. It doesn't matter. Whether you're satisfied with fraction or you're satisfied with decimal fraction, no problem. It doesn't matter. For example, I say 1 over 0.5, let's say, 0.5 square. Because it says distance becomes half. Half means 0.5 square. So here 1 over 0.25 becomes what? Right? Becomes 100 over 20. Because you have to invert this fraction, it will be 100 over 20 and is equal to 4. So the answer, the force becomes 4 times. It will be 4-fold. So which option is true? It says gravitational force would be what? Would be quarter. Is it, let's say, rational? No, it's not rational. We don't believe it. It doesn't, let's say, it doesn't become half because distance becomes half. Objects, let's say, come closer to one another. That's why in this situation, force increases actually by the factor of 2. Increases by the factor of 2. Actually, double. No, it's not just double. That's why fourfold is true. Actually, we obey the rule. We don't answer it, let's say, in a hurry. We don't answer it without any information. We have the law, we obey the law mathematically. After that, we decide. Question 22, gravitational force would vary by a factor of space if the separation between Earth and the Moon tripled. Triple means 3 times, right? If the separation becomes triple, let me do it for you again. Right now, I'm gonna, we are in question 22, right? Let me do it for you. It says if the separation becomes triple, separation means distance, means r becomes 3. So you have to write fg, right? Let me write it within this question, actually this one here. Fg is directly inversely proportional to the r square. I told you instead of r you have to write 3 because it says triple, means 3 times. So fg there's the 1 over 3 square, right? 1 over 3 square means 1 over 9. That's why let's say gravitational force would vary by a factor of 3, no, 1 over 3, 9 or not 1 over 9. So 1 over 9 is true because separation becomes triple. Objects move away from one another, let's say 3 times, let's say 3 times more than their original, let's say, distance. That's why 1 over 9 is true. Question 23, gravitational force would be space if the distance between Earth and the Moon turned to 1/3. Look here, 1/3 of their original distance. Right now, again, let's say I want you to apply this relationship for this case actually. Let me do it for you again. Here we are in question 23, and what's the condition and what happens to the separation? Separation turns to 1/3, right? Separate. I can say Fg is inversely proportional to r squared. Instead of r, you have to write 1 over 3. 1/3 means 1 over 3, and will be 1 over 3 square, right? 1 over 3 square. So it will be what? It will be 1 over 9. What does it mean? Means you have to, let's say, invert the fraction, and the answer will be 9, right? 3, 1 over 3, 9, or 1 over 9. So 1 over 9 because objects come closer and closer to one another 3 times, right? Objects 3 times closer to one another, or the separation becomes 1/3. Just put it in this relationship, and let's say you can guess the answer. Thank you very much, guys, for watching this video. I hope you enjoyed this lecture, and bye for now.